started. So I get to introduce the person who usually introduces the speaker. So I'm Katrina. I'm Moshe's thesis advisor. Moshe Shenfeld is our speaker for today. He is a PhD student who is finishing up shortly and continuing on to a postdoc. He's done really nice work on differential privacy for machine learning and privacy-adjacent topics. If you guys haven't already heard about stability of various forms, asking about stability of various sorts. And today he'll talk about some of his joint work with Charlie Feldman.
Thank you. So, as Katrina mentioned, even though she's my advisor, the two works I will present today are joint work with Vitaly Feldman. He works in Apple Research. I interned there 2 summers, and that project went on and got its own life. And though it is a relatively theoretical work, as we'll move along, you will see why it interests them also as something with a practical aspect. Okay, so let's start with like a general, like mathematical question that is like very clear and abstract. So say I'm presenting 2 ways of sampling from some distributions. So I'm starting with like 2 distributions, P and Q. All I will tell you about them is that they're like somewhat similar in some way that we will later have to represent. So process 1 is I sample uniformly out of T coordinates, a single coordinate that I will call 1 and the rest is 0. For each coordinate where I sampled 0, I will associate it with the distribution Q, and the one that I sampled 1, I will associate with P. Then I will sample a single element from each of these distributions. So I have T elements, Y1 to Yt, and I would look at the distribution of the output of this view of size T, and I will call it random allocation. Why? We'll get to it later. Okay, 1 distribution. Here's another scheme. At each step, I flip a coin. With probability 1 over T, I choose to use distribution P, and with probability 1 minus that, I choose to use distribution Q. And then I sample an element from the distribution that I've chosen. And again, and I do it T times. This process, in expectation, uses Q once, and uses P once, and uses Q T minus 1 times. But that's only an expectation. There's some probability that P will never be used. There's some probability that it will be used multiple times. We will call this Poisson sampling, for reasons, again, we'll get to a little later. And intuitively, if P and Q are similar, so it's somewhat hard to guess by looking at the outputs which elements came from sampling P and which elements came from sampling Q. So therefore, these 2 distributions should be similar to each other, and in a sense also similar to just sampling T times all of them out of Q.
And so faster, Moshe. Here you either sample from P or Q with a probability that's 1 over T.
For each iteration, with probability 1 over T, I choose P, and with probability 1 minus that, I choose Q.
So most of the time you choose P.
No, 1 over T to choose P, 1 minus that to choose Q.
So after time, you're only choosing from Q. As T increases, you
Oh, no. T is a fixed number. Maybe capital T. Both of them, T is a parameter. It's not the index. The index is I.
So let's assume T2.
Yeah.
So here, half the time you sample from P and half from Q.
Yes.
All right.
And so if you choose a single index here, the distribution is the same. Right? If I look only at the first index, it's the same. Because here I had only 2 steps. So with probability half, I chose this one to be Q, and with probability half, I chose this one to be P. The difference is that here, I definitely sampled once from P and once from Q, and here there's 25% that I sampled both of them from P.
What are you doing here on the left?
First, I'm sampling a single index out of the T values.
2.
So
T stands for 2.
Okay. So here I choose with probability half, I will sample the first one from Q and the second one from P. And with probability half, I will sample the first one from P and the second one from Q. So there's only two options. How will I assign the distribution from which I would sample the element? And here, these are two independent coin flips. So in expectation, once you go to a larger number, here I would also use a single one-time p. But there's some probability that I would use it more or less. Versus here that I will use it exactly once, and the only question is where. And obviously, the distribution over the choices of P and Q in these two processes are different. But the question is, how different are the distribution of the final outputs? So obviously, if P and Q are very different from each other, the output tells me which distribution I use. But if they're similar, how much is the whole process similar? And this is a general question, but I will motivate it. So I will motivate it through differential privacy, and I will go through the typical process that we privacy people need to go through, which is motivating privacy at all. So I would not motivate privacy in the sense of like, why do I want to maintain my privacy? Okay, that people can understand, but like the typical response I would get when I will tell the privacy stories, especially in the context of machine learning, which we would focus on here, is like, yes, but the model doesn't necessarily like remember all of your details. It's like learn the general thing. So as any smart example, XKCD did it before us. So they gave the example of like autocomplete that guesses the next tokens that are the secret information. Lo and behold, a few years later, oh, I forgot to put the reference, Carlini, Nicholas Carlini and a few other people did the following amazing attack, which is extremely interesting on its own for understanding LLMs. Here is the very sophisticated attack they did. They told an LLM, I was GPT-3, but the base model. Repeat the word poem infinitely, whatever. So that's what it did, and it replied with like, I don't know, thousands of times where it repeated the word poem, 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 poem. At some point, it completely lost context, right? It's like, it never saw a text that was just 5,000 times poem, and it just started spitting out information. This is like, they redacted it from the paper, but they got just word by word some document that was the input to their training model. So it happens. And of course, it can happen also in images. This is an example from just looking at the weights of the model. People managed to reconstruct some of the training data. If you can look at the gradients throughout the process, which sounds a bit unrealistic, but when you remember that we train now in a sort of a federated way, and people might be able to eavesdrop, you can reconstruct even much more complicated images. The networks learn somehow at least some of the samples, and if it learned them and if it memorized them, we might be able to extract it. And then if someone trained on our emails, even though they wanted to train to just learn, how do you write in English, they might have memorized our information and it might leave. Okay, so what do we do? So differential privacy, 20-year-old notion, that is a property, and this is the first point that I wanted to make. This is a property of the mechanism. A mechanism is an abstraction that says it gets some data and releases some output. I don't care what it is. It could be that it's linear regression and it releases the parameters of the model. It can be a training model. It can be someone asking what is the average height of the people in this data set. It's a process, and the process has the privacy property, not a specific response. So how does it go? So first, it requires that if we change a single element in any data set, so there's 2 points in this sentence. One is that we don't assume any distributional assumptions on the data. It can be any data set, even like a very atypical data set, and any element might mean I need to protect not only a typical user, a typical person, but also extreme people, because these are the people who typically require more privacy protection. So I change a single element. The outcome of the mechanism is nearly unnoticeable. So there's a difference in the outcome. So by definition, I need to define what is nearly and what is unnoticeable. So the way we define it is as a probabilistic process. So for this notation will mean that neighboring datasets differ in a single element. We have the following process, the following property, that this probability of the output given one data set landing in some subset is close to the other one. Why should we use this measure? So here is a verbal interpretation of this equation. So I say the following thing. We model it as some very strong adversary looking at the output and trying to use that to understand whether someone participated or did not participate in the data set, in the data that was used to train the model. So it takes some subsets of possible outputs and it says, well, if I would see these outputs, I would guess that this user was there. And well, there's some false positive and some true positive. So if it didn't leak any information, that would be just a random guess. So the true positive and false positive will have the same probability. So what we require is that they will be relatively close to each other. The parameter that I want you to focus on is the epsilon. So epsilon basically bounds the log probability ratio because it's in the exponent, just so we have a scale. So numbers around between 0 and 1 or like very small constant are reasonable, but like epsilon equal 10 is nearly useless because it means that the probability of guessing is not better than like e to the 10. Okay, that's much, much better. So just so we have in mind, because we will see numbers afterwards, like epsilon equal 1, 2, half, those are numbers that we would like to see. Okay, so far so good. Okay, so differential privacy also has a mathematical definition. It's not only a storytelling tool. And these are a bunch of notations. What matters here is that there is a divergence, a difference, a distance, but I'm using distance in quotation marks. It's not a formal distance measure between distributions that captures this property. So basically, we would see this notation in times that will be, we give some epsilon. So this epsilon defines some similarity between distributions, and we say if the output distribution of the mechanism is given one data set and given another data set are close in this divergence up to this delta, that is good. So by definition, just from the way we define it, private mechanisms must be randomized. A deterministic mechanism cannot be private unless it just always outputs 0 or something meaningless. And what we require is that these distributions are close in some sense. Okay. So let's pick one mechanism that is like a typical example, and also it's actually the private mechanism we will keep using. We have two data sets, and so elements are not a function, but arbitrary elements. But let's say we assign a number to each one. Let's say the height, right? We can think of a function from the elements to some number. So, okay, obviously if I have two data sets that differ only in a single element and I want to know the average height, it's the same up to the height of one of them. And here's what I do. I compute the average and I add some noise sampled from a Gaussian distribution with some sigma. So that means that if the output distribution of the mechanism is always a Gaussian distribution, with the mean being the empirical average of the days. So if our standard deviation is significantly larger than the difference to the average that is induced by changing a single element, well, it's as though you're getting one sample out of a Gaussian distribution, and you're trying to use that sample to guess if it's a Gaussian distribution centered around 0 or, let's say, 0.1. Right? Because we know the gap can't be too large, because the height of a person is, I don't know, between 0 and, let's say, 3 meters. And if there are 100 people, so it's 3 over 100. That's the maximal effect. Right? So this is like a simple example of a Gaussian, of a private mechanism that just says, check what is the maximal effect of a single person on the outcome, add noise that is sufficiently large to mask it, and therefore people will barely have a chance, right? If you will try to guess which Gaussian was used to produce a single element, and the Gaussians had the same variance and a mean that is very close to each other, closer than the variance, your chances will be just ever so slightly better than a random guess. And as I said before, there's the hockey stick divergence. So in the case of Gaussians, it has an explicit form. It doesn't matter what the form is. It's basically the difference between two scales of tails of the Gaussian and for different parameters. The point here is only that we have a closed form expression for it, and numerically we can exactly evaluate it. So it's a very convenient mechanism. Differential privacy has a bunch of cool properties. I will mention here two that will be used throughout this talk. One is called composition. And that says that unlike older privacy notions that worked well when you had that one mechanism that used them, but once you started adding a few calls, everything fell apart. Differential privacy has the property that if you call a mechanism that has some epsilon 1, delta 1 privacy guarantees, and then you call another mechanism on the same data, maybe even you chose a second mechanism based on the first output. You can do like relatively general stuff as we do when we train models or when we do data analysis. We can still be sure that the overall privacy leakage will not go too bad. There's some equation for that. It doesn't matter for our purposes. It's only that it can blow up arbitrarily. It's very convenient. It doesn't grow up very fast. Second property is maybe even cooler, is called post-processing, is that if I told you that this mechanism is differentially private, it doesn't matter what kind of attack you will come up with later. It doesn't matter what auxiliary information the analyst or the adversary has. It doesn't matter what will happen down the line. If the release was private, everything else will be private. So we don't need so here's just an example. So if privacy was a notion like, well, the number will be close, whether it's this number or that, whether it's this data set or that data set, like kind of robustness notion. But close number still allows for the option that a lot of information is encoded in some lower order bits. And then someone smart enough will be able to post-process it, and from those lower order bits, figure out which of the two data sets were used. Differential privacy tells you nothing like that can happen. Okay, so let's see how it affects the real world. And it does affect the real world. There's even examples as of last year of Google training a small, not small, like still an LLM, but not like the crazy large LLM in a completely differentially private manner. There are a lot of examples, like the big companies actually use it. Reminder, gradient descent. First, let's think of the theoretical notion of gradient descent. There's some loss landscape, and this is defined by some parameters, say the weights of a neural network, and we iteratively take one step in the direction of the gradient. Now, this picture represents a theoretical world where I have access to the actual loss. In reality, we don't have access to like the underlying distribution that defines the loss. So what we have instead is we have a data set, and we use it to estimate the gradients. How do we do it? We, at every iteration, when we want to know what is the gradient of this model, of the loss of this model with respect to these parameters, we sample a bunch of points, and we empirically estimate it on them. So here come the composition and post-processing points. Is notice that from the privacy perspective, I don't care what happens here. I don't care if the update here is like vanilla SGD, or I use Atom, or some very complex ways to memorize like a lot of gradients and make a much smarter step. It doesn't matter. This is where the data might have leaked. So all I need is to protect this point, and if I protected this point, all the rest is post-processing, but I do need to pay for composition because it ran several times. So what do? Gaussian mechanism. The only thing we do is we take the gradients, we clip their norm, pair element. So now it's not a single number, like a large vector, but we clip it to be in a certain ball. And we add Gaussian noise that scales appropriately. And that's enough. That simple step is enough to guarantee that the mechanism is differentially private, and therefore, from post-processing, I can release the model, I can let you query it as many times as you want, everything is okay. But there's only one point we need to remember. There's a trade-off here. I can always achieve as high a privacy level as I want, but just adding infinite amount of noise. But then the utility will be cracked. So, of course, what really matters is some privacy utility trade-off. And here comes like a very weird and unique property that privacy has. Typically, if some theoretical work anywhere in this building proves that there is something better even in asymptotics, but definitely in constants, it won't affect any product in any real world. Because if someone trained a model and it got a certain level of accuracy or utility, the fact that someone proved that I should have done it better or worse won't affect it. This is the quality of the product. The proof guides us in what kind of techniques we will try to use and what attempts we will make, and maybe we will know, oh, that direction is pointless. But if someone proved that the VC dimension of some problem is half of what we thought, it doesn't have an effect on what the quality of a concrete algorithm is. In privacy, improving a factor 2 would make a difference. Why? Because if the company decided to commit to releasing their information with epsilon equal 0.1 because they want people to trust them, and now the best proof that we have is that in order to get epsilon 0.1 from this whole process, you need to add noise like, 7.3. So that causes some degradation in quality. But if I improve the proof, and now I show that even sigma equal, 5 is enough to get the same epsilon, great, they now need to add less noise, and all of a sudden the model is actually better. So there's like a very unique property that the proof is sort of affects directly the product. So privacy people really try to squeeze anything they can out of any source of randomness in the process. And the source of randomness we will focus on in this talk is this sampling step. Okay, so there's privacy. Within privacy, there is DP-SGD, the specific algorithm for making a machine learning optimization private. And within that, we will focus not on changing the type of noise or anything like that, but on how do we sample and how much privacy do we get out of it. Okay, so again, from privacy perspective, we will just abstract it away. There's a data set of size n. There is a sequence of t calls to some private algorithm that maybe is affected by the previous outputs. We need to split the elements to be used between the calls to the mechanism in some way, and we want to analyze the privacy loss of this entire process. So I will start by giving one way of splitting it, which I want you not to keep in your mind as the mental model of what's happening. This is the atypical case, and that is if the order of the data set matters and is public. So imagine, here's a very simple case, if n is equal to t, and I just use the first element to estimate the first call, the second element to estimate the second call, etc. In this case, from the privacy perspective, there was no long process. There was only a single call, right? If I change element I, then, and I want to guess if element I is one option or another option, I just look at the ith call to the algorithm, and that's the only thing that matters. So there is no additional randomness from the sampling that we could leverage. So this is not the kind of models we would use. From now on, we would always implicitly assume the data set is unordered. We don't really assume it, we just enforce it by adding some kind of sampling that is order independent. Okay, so here's the second option, the option that we're most used to, and this is what actually people do anyway in SGD. They need to sample in some way. They just shuffle the data. So again, in this case, the data set is the same size of the number of calls. For simplicity, that is equivalent to batch size equal 1 and a single epoch, if you think in terms of machine learning. I permuted the data in some random way, and now I use the first permuted element, the second permuted element, etc. This is what people do, and it's very practical. It has good utility. I mean, there's a reason why people use it even without privacy, but it's much harder to analyze, and we know that in certain cases it gets slightly worse privacy. Soon I will say some bit more damning evidence, but like a few years ago, the idea of using DP-SGD is 2014, 2016. This is when this mechanism was proposed. And we knew that shuffle is a bit more tricky, but like that's the practical thing. So the theory of privacy used a different sampling method called Poisson sampling independent. What does it mean? It means that at each step, for each element, I flipped a coin. It could be any probability, but here, in order to have like expected batch size 1, so we can align the two options, so I would choose the probability to be 1 over t. So we flip a coin, we assign elements. Some mechanisms get more than one element. Some calls will get 0 elements, and then it's as though the average gradient is 0, and then you add the noise. Some elements will be used once, some elements won't be used at all or more. And it's very easy to analyze. Everything is independent. Everything works very well. You do composition between mechanisms. You do independent sampling between elements. Everything is great. Privacy is really nice, as we will see. It's not practical, and it has problems on 2 levels. One is on a very technical level. The size of each batch is now not fixed. And compilers and everything go crazy for that. We can do some tricks to solve it. Let's say we say, well, in expectation it's going to be a batch of size 1, so we will allocate 10. The probability of exceeding 10 is very low, so we will pad it with 0. We have some tricks. Not great, not terrible, but the utility is worse. Intuitively, it happens because now, so for example, in this, if I run this one epoch, we have 1 over e probability. For any element, we have 1 over e probability that it will not be used at all. So on average, we lose a third of the elements. That definitely causes some utility degradation. We have all sorts of other problems I won't get into. Okay, so these are the 2 options we have. Yes?
Every A quantity is the batch, right? You're saying? And
it's the gradient estimation based on the batch. So the batch is which elements got in. And then A is already the process where we say, well, this is my model. These are the parameters of the model at this point. What is the average gradient on this batch? I compute it, I clip, I add noise, and I release it. But again, we can abstract. The privacy analysis has nothing to do with the fact that this is DP-SGD. It can be any code.
What would you want the probability to be 1 over t without batches? Why not increase the probability or decrease it to try and change the probability of each element being each batch?
So I can choose it to be whatever I want. I chose 1 over t just to align it to the previous example where we shuffle. So I chose, also for shuffling, I can choose n and t not to be the same. Right? The ratio between n and t will be the batch size. I chose it to be the same just for simplicity. So we would say, so here, every element is used exactly once. And here, because I want to make it comparable, I need to have an expected batch size that is the same. So if I have t calls, if I want probability that makes the expected batch size 1, so it has to be 1 over t. Okay, so let's put some numbers. So here's the plot that will be running example. So let's spend a moment to understand. So the x-axis is sigma. How much noise did I add? And the y-axis is epsilon. I fixed the number of elements the number of calls to be 10 to the 5, and delta to be 10 to the minus 6. Remember, delta is like a very small event that things go really crazy. I didn't choose these numbers. These numbers came from a paper that showed the big problem, which we'll get to in a few slides. So let's see why this makes sense. I said small epsilon is better. Small epsilon means that the probability of false positive and true positive are close to each other, meaning I'm closer to a random guess. 0 is truly random guess. So we're not surprised. If we have the fixed example that I chose at the beginning, that I showed at the beginning, where I know which coordinate was used, this is basically the privacy accuracy, in a way, trade-off of a single call to the Gaussian mechanism. So add more noise, get better privacy. Obviously, the further we move to the right will probably degrade utility in some way. I don't know to say how, because that depends on the specific algorithm you're using it. But clearly, the more noise we add, at least beyond a certain level, the worse utility we get. Okay, trade-off is not surprising. How much does this sampling part that I said, hey, we can improve the analysis, the privacy guarantee, by noticing that there's some uncertainty which batch used which element. So let's say I use the Poisson analysis. That's much better. So basically what we see is for the same level of noise that I had, I get way, way better epsilon. Or if you flip it, if I want to get a certain level of epsilon, I can get it with adding much less noise. So this is great. What does shuffle give us in this setting? So here is the best thing that shuffle gives us. Oh, you don't see the line? That's because it's exactly the black line. In this regime, which is it's not the typical regime, but it's definitely not a completely atypical regime, the upper bound that we had was no better than the deterministic case. Had I shown the plot going further to the right, around 2 or something, shuffle starts getting better and gradually gets close to Poisson, but for way larger bands of sigma, and it doesn't get, it never gets to Poisson. There's always a gap, asymptotically even not negligible gap. Okay, so this is what we knew around, okay, we first had the analysis for Poisson, that's 2016, then the analysis for shuffle came 2018, 19, we had upper bound, we knew there's a gap, and for a while, people wrote in the papers, look, the experiment was ran with shuffle because Poisson is problematic, we know that there might be a gap, and everyone hoped that this is just a matter of analysis of upper bound of shuffle that's not tight enough. And then 2 years ago, in ICML, this group from Google managed to find a lower bound for the privacy of shuffle, and it turns out to be much worse than we hoped. So let's have just a concrete number. So let's say you chose to add noise sigma equal 0.6, and you said, well, I did shuffle, but I did the analysis for Poisson, probably they're about the same. So you thought the privacy is, I don't know, 0.5 or whatever it is, and in reality, your privacy was about 8. And again, reminding you, this is an exponent. So it's e to the half versus e to the 8. That is a big difference. We're really in trouble. So basically what this tells us is that we are not only taking a risk in using one analysis and implementing it in a different way, we're cheating ourselves. So this opened sort of a race to figure out what can we do. I mean, can we at least know that in a certain regime there is no problem? Can we have a third version? And this is basically where the part of our work starts is we will consider a third sampling scheme. Okay. So let's just understand how should we align Poisson and shuffle. So in our sampling, we could have 2 aspects that have or don't have correlation. Different elements and different steps. Meaning, if I know that a certain element participated in a certain step, does it change the probability that a different element participated in the same step? And does it, this is the columns, and does it change the probability that this element participated in another step? These are the rows. So Poisson sampling, where I said each element at each step flipped an independent coin and decided whether it will participate or not. That's Poisson. Shuffle, everything is correlated, but there are 2 more options. I won't go into this one, it has pros and cons of its own. This is the one we considered, random allocation, also known as balls and bins. There are a few papers coming out at the same time, each one showing some different aspects. Okay, why should another sampling scheme will be interesting? So, just let's define it formally. So, random allocation, 1 out of t means every element uniformly samples an index where it will participate, but independent of other elements. So, dependence between steps, not between elements. And k out of t allocation, which is the notion that only we analyze, is every element chooses k uniformly. And I would claim that it has best of both worlds, better privacy and better utility.
So they could end up choosing the same.
Yeah. So the only thing that can happen is the same element can participate twice. The k choices are sort of dependent in the sense that you uniformly choose a subset of k indexes out of that. but now we're claiming it has better privacy and better utility. Better utility, they ran a few experiments. Don't need to understand the whole plot, but what you should see is just there's shuffle, that's the red, balls and bins, that's a random allocation. It's the blue, you see the utility is about the same, and if I use Poisson, in some regimes it's much worse, in other regimes it's also worse, but it's a little hard to see because of the scales. So yes, it's as good as shuffle for utility, at least in a bunch of experiments that they and we did. Okay, what about privacy? So what they did is, don't try to go into this plot, it has like a ton of lines, but what's important is they showed that empirically, they did some Monte Carlo simulation in order to estimate. It seems like the privacy level of random allocation is about as good as Poisson, and even in some regimes, slightly better. But they didn't provide any analytical bound. So we know it has good utility. We have very good indication that it has good privacy, and that's where we are. So,
can you go back to the one? Why does the Poisson have lower utility?
Oh, so there are a few things, but probably the most important effect is the fact that the number of times each element participates is itself a random variable, and it adds another source of noise that, besides the fact that it contributes something to the privacy, it also decreases accuracy. So again, let's think of the example of a single epoch. So if each element participates at each step with probability 1 over t, and there are t steps. So an average, the probability of each element not participating at all is 1 over e. So almost a third of your elements you didn't use at each step. Well, like giving up on a third of your elements is non-negligible. And then you have also elements participating many times with some probability. So if you're unlucky that it's like an atypical element, it can completely derive you, push you in a weird way. For clean examples like mean estimation, we can show it analytically.
The SGD on average, the gradient is correct. You're saying the variance is much larger.
You just added variance that for no reason, in a way. Look, the difference is not crazy. I'm not claiming that it breaks everything, but it's wasteful, and so combined with the impracticality and the fact that we know it ruins utility, we don't like it. It's not like it's impossible. Opacus implemented it in the PyTorch option. It is doable. It's not impossible to do. Yeah.
Do we always choose one of the t for the Poisson?
No. It's I'm choosing. Same way in shuffle. Also, we're not using bet size of 1 necessarily. Everything here is just a simplified example, so everything will be easily aligned. Otherwise, I'll just need to have like a bunch of extra parameters for no reason. Any other questions? Okay, so again, back to some mathematical tools. So I will introduce a notion called if you know what's the stochastic domination, it's like a relative of stochastic domination, but it's not the same. Stochastic domination implies this domination notion, but not the other way around. So I would say a pair of distribution PQ dominate another pair P prime Q prime if this hockey stick, right? The hockey stick is a function. I give you epsilon, I get a delta. So if this whole function is an upper bounds the other function. In the same way, I can say a pair of distribution dominates a mechanism, and that is if for any pair of neighboring datasets, this is neighboring, the pair of distributions induced by this mechanism and these two datasets is dominated by this PQ. Why is it interesting? Because it means that because of this hockey stick property and because privacy is defined with hockey stick, it means that instead of now analyzing the privacy of any pair of datasets and trying to go into like, well, there could be all sorts of weird datasets, there's only one pair of distributions I need to analyze. I do any accounting both theoretically and numerically on this pair, and life is much easier. So for example, for the Gaussian mechanism, it can be multidimensional, I can clip things, I can do all sorts of weird things. The dominating pair is just a pair of two distributions. So it doesn't matter what the distributions are, it's basically two Gaussians that are also shifted, just the role of the variance flips, but we have a concrete closed form. And this is a very useful tool because it has a bunch of properties that sort of explain why Poisson scheme is so useful. So first, if I know what is the dominating pair of a mechanism, and I have a Poisson sampling, I know what is the dominating pair of the Poisson sampled a single sampling of Poisson. So if once I flipped a coin and I call it, like if I look at any specific iteration, I know the pair, and it's basically a mixture distribution. I put here an asterisk, and I'll put it a few times. There's some subtlety if by replacing an element, I mean I replace one element by another element, or do I mean adding and removing? And if I mean add and remove, then this is asymmetric relation, so I need to define both the effect of add and remove. Just saying it so people won't be misled. For all intents and purposes, the story is the same story. Another cool property. If a mechanism is dominated by a pair and another mechanism is dominated by another pair, if I compose two mechanisms, it's dominated by just the product of these two distributions. And the cool thing is these products are no longer dependent, and so I don't even need to go into too many complications and computation of this pair. So, for example, that means that the entire Poisson scheme, I can write explicitly the dominating pair of the Poisson scheme. So all I need to be able is to compute the hockey stick of this pair, and that already upper bounds the privacy of the Poisson scheme with, let's say, the Gaussian mechanism. So analysis is relatively nice. This is basically why Poisson works so well. So the question was, what can we do for random allocation? So we identified the dominating pair for random allocation, and we have two steps. One is we say, first, if we sample k out of t, we can reduce it to composing k times sampling 1 out of t over k. So this is like a fancy way to write it. Like this is the k composition, and I say basically if we knew how to analyze the privacy of 1 out of t for some t, let's say t prime, I can use it to analyze k out of t by just breaking it down to two stages. Okay, so already the story is simpler. So now what do we know to say about 1 over t? Well, this is a dominating pair. So if mechanism M is dominated by PQ, then random allocation of sampling 1 out of t is dominated by this t. What do we have here? You run over the possible indexes. One of them you use for P, the rest you use for Q. You use Q, this is uniformly over T options. Sorry, there's 1 over T for that here. And there is versus just using Q. Okay, so at this point, it might still start ringing bells of why did I propose those two distributions at the beginning of the talk. Okay, so we know what are the dominating pair. How do we use it? So here are two cool insights. They're both basically the visual representation of a mathematical proof. Insight number 1. Let's look at random allocation. So again, what is the process representing basically not the Gaussian mechanism random allocation, but the upper bound, the dominating pair. So there's T calls to the mechanism. 1 out of them I will use P. P represents that iteration where I did use the element, and Q represents the distribution when I didn't use the element. And the problem is the outputs are correlated because, as I said, the choice of each step, the choice of distribution at each step is not independent of other steps. That's the downside. Well, let's think of what happens in the first step. The first step is a Bernoulli 1 over t, right? Because there's a chance of 1 over t that I chose p here. My point is that in the rest of the steps, the output distribution of y can be thought of as something different. Imagine I continue to do this Poisson thing every time I sample from a Bernoulli distribution, but the probability is no longer 1 over t. It's some function of the previous outputs. Doesn't matter what the function is. My claim is that for a certain function of previous outputs, this posterior sampling induces the exact same output distribution over the y's as random allocation. So obviously the probability of sampling P or Q is not the same, right? Because here definitely I used Q once, and here it might be more or less. But the output distribution is the same. Why? Because I would choose the probability to sort of cancel things in the base rule. This is basically a glorified base theorem. And I can choose the probability such that it's going to have the same output distribution. And therefore, the privacy properties of this algorithm and that algorithm are identical. So all I need to prove is that with high probability, this remains close to 1 over t. And then what I can say is that basically random allocation is Poisson, just with sampling probability that is not exactly 1 over t, but a little further away. So this is one thing that we prove. In the other direction, Poisson is sort of random allocation in an interesting way. Because we can think of Poisson as the following properties. Step 1, choose from a binomial with parameters t and 1 over t, how many times I would use q. Once I fix how many times will I use q, this is just a random allocation with that number of times. So basically, we can treat the Poisson sampling as a two-step process where I first decide what will be my k. I sample it from some binomial, and then I output from that mixture. So we have two formal analyses that are represented in these pictures that tell me that random allocation is Poisson with a trick, and Poisson is random allocation with a trick. Because here also we know how many times will the, what is the distribution over k, right? Like typically it's 1, some probability 0, and it decays very fast to be higher. So we have basically 3 results out of it. First one saying that random allocation is no worse, its privacy is no worse than a t-step Poisson with sampling probability k over t times 1 plus little o of 1. Another parameter that little o meaning with respect to t. So as t grows, the similarity between the two becomes exact. And this is, I'm writing it with little o, and we have the explicit form of the rates. Second insight is that there's a constant, say, and this constant comes from basically 1 minus 1 over e or something like that. That sampling probability of, like, how does binomial with t, 1 over t behave? This is where the Poisson name comes. So this is asymptotic, this is everywhere. And there's a third technique that I won't go into that uses another privacy technique. Why did we use these 3 techniques? Because, so I really don't want you to try to read into this. This is a nightmare to explain. But what's important is that this is an example of a very large range. Look, xm starts at 100, which is ridiculous. But it just shows the fact that there are different regimes where each of these 3 techniques provides a better analytical bound. Let's look at what does it make in reality. So now we're back to that plot, reminding again. This is what we get if we use no amplification. The orange one is what we got when we used Poisson. And the green one, the dashed green one, is a lower bound in what shuffle gets. So here's what we get with random allocation, the blue line. Generally speaking, about the same as Poisson. And you see this interesting phenomenon. There's a small regime where it's even slightly better than Poisson. Then there's a regime where it's just like a constant worse, and asymptotically they become the same. It's harder to see that it's asymptotically because it's not linear, but trust me, they really become the same asymptotically. So everyone should be happy and move on to the next research project. But as I mentioned, the proof is the product, and this constant means that, when you put the numbers in, especially if we compose over a large number of steps, as it's typically done in real world, you pay here a constant, like factor 1.5, 2, whatever. 1.5, 2, it scales with noise, sometimes even worse. That's more noise that no one wants to do. And reminder, if we look at the plot that I showed before when they did this Monte Carlo simulation, it looked like they're exactly the same, and maybe even allocation is slightly better. So we want more. So we did more. So one last mathematical tool that we would use called privacy loss distribution, PLD. Here's an insight. I have 2 distributions, and I have some element in the output domain of these distributions. So I can define a function of this output, which is the low probability ratio. This quantity appears in so many places in theory of machine learning and information theory, it's typically called information density. In statistics, this is optimal decision rule. It has all sorts of interpretations. Intuitively, it basically tells me, for this particular element, how much did it help me distinguish between two distributions, right? So there could be elements that it's about the same, could be elements where it's very different. So because this is a function of a random quantity, I can say, well, if I'm sampling omega from P and then computing this privacy loss, I have a random variable. So this is the random variable, the privacy loss random variable, and its distribution is called privacy loss distribution. The important thing is that we can represent the hockey stick property that, again, reminding you is what quantifies privacy. We can express it as an expectation of some function of this random variable. So if I know P and Q, I can compute these random variables, I can compute this expectation. And the cool thing is, as a result, what happens is that the composition becomes convolution. So now it's a matter of computing convolutions, and convolutions we know how to compute. Of course, we need to be careful. If it's in a computer, so it's not the real distribution over infinite support, so we need to discretize it, and we need to discretize it the right way. We know how to do it. It doesn't cost too much computationally, so we can track numerically this quantity instead of just using analytical bounds. And we all know that computing something numerically can be tighter than just the analytical bounds. So what we did is we showed, and you can see some similarity in the way the dominating pair looked like in this privacy loss, what it looks like. But basically, the important thing is we say you can think of the privacy loss distribution of the random allocation as a post-process of the original privacy loss. So again, we can compute it. Notice here it's sort of a convolution of exponent of the PLDs, which is like a weird creature which causes a lot of technical problems such that you can't use FFT anymore. But again, it was annoying, but the end result is that we have an algorithm that computes it in a way that is quadratically inverse in the error that we want. The alpha and beta are like how much accuracy I want, and epsilon and delta. So I basically get epsilon up to alpha error and delta up to beta error. So the fact that it's quadratically inverse in alpha is annoying. The fact that it grows only polarly logarithmically in t is great, because that is the number that's typically really high. Works very well. And yay, our line is the lowest, which is what we always want in machine learning. And it's not only the lowest now, we have a lower bound also. So we know, and I didn't draw both of them. The lower bound is the same. We got a complaint in the review of this paper that you can't distinguish the two lines of the upper and lower, and we responded, thank you for the compliment. What can I say? So yeah, we're happy and it's good. So I'll just do like a brief summary. So just going back to what was the bigger story. So we had some toolkit for privacy analysis that is basically the thing that people do these days. And that toolkit had great theory and practical implementation, but they were not the same. And for a while we thought like, okay, we just need to squeeze theory a little better. And then we realized, no, there's a real gap. There's a problem. So people came up with a few groups simultaneously with this new sampling scheme that seems to be the best of both worlds, but we were sort of missing the proof for the improved privacy results. And what we provided is like both the theoretical, the analytical bounds, and then the numerical type bounds that show that there indeed we are in this great world where the privacy of random allocation is about as good and typically slightly better than Poisson. On a more general level, we created here a toolkit for asking how are two sampling schemes related to each other. And And this toolkit is probably relevant in much broader sense. Because people care for these abstract types of distributions in many cases, but more generally, it's because we know that differential privacy is essentially a stability notion. And by that I mean that it guarantees that the output distribution of whatever the private process is not affected too much by changing a single element. And that property is a desired property for many other reasons. This sounds like because it is related to robustness, it's known to protect against overfitting, because just on a very intuitive level, overfitting means you tailored your hypothesis or your model to the specific data set. But if I protected the privacy of the data set, then it can't be that you tailored it to it, because otherwise you're revealing the identity of the elements. So we want these ideas in many cases, and so this toolkit can help us do that for other use cases. And when we think about why does it work, so basically what it tells us, it's a lesson in a broader phenomena where we notice that many of our learning algorithms, so I'm not going to surprise anyone here if I'll say that theory is somewhat lagging behind practice in many of these big questions of like, why do large models manage to predict very well things even on test set, why they don't overfit. We don't see a lot of problems that theory tells us that might occur in these settings, so which means there's some property of the world we live in, whether it is the algorithm that we use or the distributions that were handed to us, right? Like we don't, the distribution of images in the world is not necessarily the worst case distribution, and the algorithm that we use is not the worst case possible algorithm. And we need to work a lot to understand what is this property of these distributions and these algorithms of the settings we're actually living in that explains why things work better than expected. And one of the families of explanations is that, in fact, there's a lot more randomness in the processes that we create that we don't necessarily understand how to analyze. So let's just take the example of DP-SGD, so of even SGD, right? So we initialize the parameters somehow, typically in a random manner. Who knows how much protection and how much stability this gives us? We sample the elements. Who knows how much stability that gives us? And how do we sample the element? I would assume most practitioners are like, yeah, I shuffle because, or maybe even they don't know they shuffle. They just call whatever is the function of the. And like people typically don't bother thinking about this subtlety unless there is something calling them to do it. And in a way, privacy forces us, because we need to prove every tiny thing even up to the content, forces us to ask ourselves very carefully, well, what happens if I sample in a slightly different way? What happens if I initialize in a slightly different way, etc., etc.? And this toolkit hopefully will be useful not only in privacy, but also stability, generalization, and so on.